So today I'm going to be talking about the role of target network in reinforcement learning. This is a presentation for our ICML paper that will be presented at Vienna later this year. Now, for those of you who are in rush, I'm just going to directly go to the algorithmic contribution that we propose in this paper to make life simple. And really, the core of what we are presenting and our insight is that we want to update the target network in reinforcement learning by minimizing the difference between the target and online network in the function space. And this stands in sharp contrast to the previous work that updates parameters of the target network, sort of in the parameter space based on either heart synchronization and polyac. Now, to parse that a little bit, let's take a look at this example. This pseudocode, you could think of it as pseudocode for either TD with target networks or the DQN algorithm or Rainbow, etc. And really, at an abstract level, these algorithms could be thought of as iterative algorithms, where at each iteration, we have this update to the online network. So we actually minimize this function h over its second input, in this case w, and the function h is really some kind of a Bellman error. In this case, squared error, but could be slightly different. And we are decoupling the target and online network. Now, once we have the online network, in the case of, for instance, DQN, we do this sharp, or rather hard synchronization of the two networks. So if we have the online network, we just set the value of the target network to the online network. And then we move to the next iteration. And so this is the hard synchronization that I was talking about. Now we could generalize this slightly, and that's the idea of polyac, where we sort of maintain a moving average of the online network by having this new beta parameter, which this would actually sort of reduce back to the case of hard synchronization when we set beta to 1. Now, what we are going to propose in this paper is that instead of doing this, we are going to update the targets network based on some discrepancy between the values of the online network and the targets network. So rather than updating the targets network in the sort of parameter space, we are going to take a look at the difference between the two networks in the function space and update the targets network accordingly. Now, again, similar to the updates to the online network, we could sort of minimize this error, or at least approximately minimize it using gradient descent. And that's the actual practical version of the algorithm. Now, if you want to sort of understand why does this make sense, well, then you have to be more patient and listen to the rest of the presentation. Now, let's be a little bit more concrete about our terminology. Obviously, we are in the Markov decision process setting. We have states, actions, ruled bars, transition probabilities of and gamma. And the core ingredient that we are interested about is this value function, which is a long-term measure of goodness of a state, or it could be a state action pair. For simplicity, we just denote that for states here. And we are in the approximate world, right? So we have this value function whose size, could think of it as a vector, whose size is extremely large because we have so many states, and we can't represent this using a lookup table. So we are doing some kind of an approximation. Could be a large language model, could be sort of a more typical feed-forward neural network. Whatever it could be, we are actually approximately trying to learn the value function. And the object that's going to really help us is our favorite Bellman equation, which is sort of recursively writing the value function in terms of a particular state, in terms of the value function of all the other states. And what we really aim to do is to sort of find this parameter theta where this equality holds, right? So we want the value function when we apply the Bellman operator to this approximate value function v theta, we get the v theta sort of vector back. And to be slightly more precise, this is the desirable set of parameters in the space theta that we are chasing for. And we call this F single for a reason that becomes obvious momentarily. Now let's take this set F single and let's think about the sort of the previous algorithms that I introduced in the second slide. So the important realization we have in this paper is, whereas we sort of define the ideal set of parameters in the space theta, the actual learning is often performed in a lifted space, theta times theta, right? So recall these two algorithms, we actually learn this online network, and then we also actually learn this target network. So learning itself is being performed in a lifted space rather than just in this space theta. And again, to recall, this was a definition of H, some kind of a Bellman error, which we could easily write in vector form. Now, if things go well, sort of like the best case scenario for these kinds of algorithms is the following. Under some assumptions, we can say, hopefully, that these algorithms converge to a point in the following set. A set is one where we actually satisfy the Bellman equation, and also these two weights must be similar, right? Because we are doing these updates, we are synchronizing them. So for the algorithm to converge, for there not to be any sort of move to the weight vectors, they need to be the same ultimately. Now, let's think about this set a bit deeper. So let's take an example. So let's say that we have this pair of weights, theta and w, where we actually satisfy the Bellman equation. So we actually satisfy this, but not with two weights that are exactly the same. These two weights are different. Now, in some sense, this is almost what we want in the sense that we do satisfy the Bellman equation, but we are kind of cheating. And the reason for that is we are actually, since the two weight vectors are different, then the resultant value functions could also be different. So the two value functions v theta and vw we have on the either side of the equation, they can be different. And so that's not the definition of a fixed point. It feels like we're cheating here. This is not an acceptable point. But now let's take a second case. So in this case, things get more interesting. So now let's say we do satisfy the Bellman equation, but we also satisfy this equality that v theta is going to be equal to vw, even though the two weight vectors are not exactly the same. So we satisfy the Bellman equation, and we are also learning just a single value function. So we satisfy this equation without any cheating. We are not learning two different value functions on the either side of the Bellman equation, even though the parameters themselves are different. The parameters are different, but the resultant value functions are the same. And so I would argue, and really this is the argument of the paper, that this is a perfect situation. This point theta and w is a perfectly fine solution to the original formulation. So if you think about the slightly more general set that we are interested in this lifted space, it's one where we actually satisfy the Bellman equation and also have the two value functions resulting from theta and w be the same. So let's juxtapose these two sets. What we are now saying is let's substitute this sort of constraint, the parameter space. It seems like this constraint is really not necessary. This is one way to enforce the equality of the two value functions on both sides, but it is actually tossing away perfectly valid solutions. The more general way of enforcing this notion that we want to learn a single value function is by just directly enforcing that in the function space rather than in the parameter space. And so really, if you think about it carefully, we will notice that any solution in F pair is also included in F value, which is the set that we are going to work with. But the converse is not true. There are perfectly valid solutions in F value that are not included in F pair simply because the two parameters are different, even though the value functions are the same. And so F value constitutes a more inclusive solution characterization for the original problem. F pair is in fact tossing away perfectly valid solutions like I mentioned before. Now then the question is, given that we have defined this set, this more general set F value, then how can we actually learn a tuple, a pair of weight vectors theta and w that belongs to this F value set? And the answer is the look-ahead replicate algorithm that I presented in the second slide, and we are going to go back to. So look-ahead replicate is the algorithm that we present in this paper. We are updating the online network exactly as before, exactly as how TD with target network and DQN, etc. Do it. But then we have this divergence from the sort of common practice, where we actually update the target network by minimizing the discrepancy in the function space of the online network and the target network. Now we have a theorem in the paper that actually proves that this LR algorithm indeed is capable of finding a solution in this F value pair and actually does so linearly, which is very exciting. And here's an example which we think is very good for illustration. So let's say this example, we have only two states in the MDP. So there is an actual, I should say, Markov chain that we identify in the paper. And when so we have two states. So the value function is just a vector in this 2D space. And we have three parameters to represent the two value functions. So when we actually start, we can see that the two value functions are different. And these are the iterates of the LR algorithm I should mention. Eventually, we can see that the two value functions actually converge to the same point in the function space, I mean, even though the parameters are different. So this actually is a situation where we converge to a point in F value. Existing algorithms would not consider this pair of parameters a valid solution just because theta and w are not the same. But this is a perfectly valid solution and one that LR algorithm is capable of finding. We actually also explore large-scale experiments with LR. In this case, we augment the rainbow algorithm with the LR-based update to the target network, and we see performance improvements both in terms of mean and median on 55 Atari games. Please take a look at the paper for more context. Now, to conclude, we argue in this paper that the common formulation is actually limited in that it excludes perfectly valid solutions because of enforcing this second constraint in the parameter space. And we actually identify a more general formulation that substitutes this parameter-based constraint with a value-based constraint. And we actually also identify an algorithm to find a solution in F value. One really exciting future work that we are thinking about is actually even go beyond F value. If you think about the set F value, then we notice that we don't really even need the two parameter spaces to be the same. That is, the hypothesis class for the target network and the online network could also be different, so long as we eventually are able to satisfy the Bellman equation and also make sure that the two value functions are the same. We don't really care what's the exact size of the number of layers of the online network and the target network, or that even they have the same architecture, or even maybe one of them is a decision tree or transformer, the other one is a feed-forward network. We are really agnostic to that. And it would be really interesting to explore that under the LR algorithm and notice that under sort of more traditional TD with target network, DQN, etc., family of algorithms, this doesn't really make sense because these algorithms update the target network in the parameter space. And if you have two different architectures, we simply cannot do this. But now under LR, this is doable. And that's it. With that, I conclude my presentation and thank you for your attention.